So first and foremost, we should finish grading your exams today. So you'll hopefully be able to get a grade, and those should be returned to you in your lab. Okay. That's the first thing. The next thing is that we should hopefully be able to. Oh man, that was the 1068 lectures always give me some really weird troubles. Keep changes, awesome. So full screen preview, boom. Okay. So the next thing is we're basically grading the add and remove functions for the sorted linked list, and I did not give you enough instructions on those, like as to what I wanted you to use. Like I didn't want you to be able to use the get node function in that one, but I didn't specify it, so I can only just the most I'll penalize is like half a point for those. But it's just I thought I was being clear with the add and remove functions, but oh well. You know, now I know for next semester this is what happens when you have guinea pigs, and most of you were able to do that pretty well. The analyses were almost all pretty good. Like one or two people got only half credit on them because it's pretty easy to get the 7 points on the get and set, and then get partial credit on the rest. But pretty much everybody got the average, like the most people got somewhere between 16 and 20 points, right, for those questions. The reverse string was apparently pretty hard. And just to mention, while there is no reverse function in string. Sorry. So anyway, that's all I'll say about that for right now. But it's given me some valuable information. But the most valuable information was the stuff you turned in at the end. So first thing was the ear mount marking, basically timestamping stuff. That was one valuable thing. I will be going through those in a video, and I'll address those all. That's what I plan to do, go through all the suggestions and address them in a video. It was, so timestamping the YouTube stuff. That's a lot of work for me. I don't know if I'll be able to do that. But one thing that I'm going to be trying to do is that come April, there will be a couple of flipped lectures, which will resemble something more along the lines of this, only that you're expected to watch some videos before coming to lecture. So I'll let you know about those well in advance. And typically those videos will be something to watch over the weekend. So, but when that happens, each topic is kind of going to be broken up into 10 to 15-minute videos, so that'll be simpler. But one student did suggest to move the camera capture up to the top right, as you can see. So I did so because now you can see the clock down there. So that helps. So I did take that. So I do read your suggestions. I do take them seriously. People want more interesting problems like the maze solver, and I will be pleased to tell you what your new problems are going to be coming before spring break. So I'm going to actually, yes, so I will assign you something over spring break. I will be assigning you something this Thursday and Friday. Do I expect for you to work on it over spring break? Not very much, right? I understand that you're probably not going to do much work on it. So basically, from my consideration as to when for due dates and stuff, spring break just isn't going to exist, right? It just doesn't count in terms of things. So the first problem that we're going to need, that I want you to solve, that you're going to get in your official write-up, is solving one of two chess problems. So, which I've talked about. And the first so let's go ahead here, called recursion. So this is the first. So I've got to redo this because normally I have towers that annoy, but I decided to put a much more interesting problem in for you guys. Okay. The first is you get to solve one of two problems that use backtracking with recursion. Now you've already had some experience with that by doing a depth first search, by doing the maze solver. Okay. But this one will involve chess, so that's going to be a bit different. And we'll go over the algorithm, which is basically for every single choice, if there's no choices left, then you're done. Okay, for every possible choice, make the valid choice. Well, we'll go over that. But let's get into the problems that I want you to solve. You choose one of these two problems. The first one is the 8 queens problem, okay, which is given, so in chess, there's this problem where basically the question is, how can you put 8 queens on a chessboard such that no queen can capture one another? So queens are the most powerful piece in chess. They can move like a rook, and they can move like a bishop, which means that not only can they move in any direction, vertically or horizontally, they can also move diagonally and capture any piece that they collide with. Okay? And basically, once they collide, of course, they stop, right? They can only hit a single piece, for those of you who don't know how to play chess. So the idea here is putting, for the 8 queens problem, since they can all move vertically, horizontally, and diagonally, the 8 queens problem asks, can I place 8 queens on a chessboard such that no queen can make a single move and capture one another? So here is a solution. There's a lot of different solutions. This one's for an 8x8 chessboard. And the idea here is that basically that this queen over here, right, no other queen shares her row, her diagonal, or her column, right? So she can't capture any other queen. So each of these queens actually cannot capture any other piece because none of the other pieces on the board share her row, column, or diagonal. So the question is, can you write a computer, a little program that solves this problem, that produces a solution? You don't have to produce all the solutions, also because a lot of the solutions, and I think there's like 92 or something of them, are just rotations of one another. But this is a solution, okay? So placing 8 queens on a chessboard, and you're more than welcome to test it on a smaller chessboard first and then scale up. I highly recommend storing your chessboard as an 8x8 integer array, so a double array, and basically using zeros for the presence of a queen, for the lack of a queen, and 1 to indicate there is a queen. And you don't want to mark any other spaces like threatened or anything. You just want queen or no queen there. If you try changing like spaces to say that space you can't place anything there, once you have to pick queens up because you realize you put a queen in the wrong place, it becomes really messy. So yeah, hint, only 1 queen can be placed on a column. That's the hint there, but I'll show you the algorithm going on. The knight's tour is the more challenging of the two problems, the chess problems you can solve, which is given a single knight, we want to do what's called a knight's tour. We place a knight on the board anywhere we want, and then we move him until he hits every single square on the chessboard exactly once. Basically, and the knight moves in a specific way, which he can move 2 squares horizontally or vertically, and then 1 square in the axis it did not move in. So it creates we always say he moves in like this L shape, and here's his moves below. So he can move 2 down and then to left and right, or he can move 2 to left and right, or he can move 1 and then that way. So there's all sorts of ways he can move, which makes it really interesting. And he can also just hop over pieces, which makes him cool. You can start him anywhere you want to. In fact, that's part of the challenge, is figuring out where you need to start him. And then your output should either be the chessboard, but with every square marked by a number to designate what order it was visited in. So the first move would be like 1, the second move would be like 2, and so on and so forth. Or listing the moves in chess notation that they make. Now, this one I highly recommend starting out on a smaller board, smaller than the standard 8x8, because the search space for this one is pretty deep, right? Just the amount of basically the amount of choices you have to make. Now, formally, I would do the Towers of Hanoi, but we went over that in class, and I feel like it's not a worthy challenge, really. So let's go ahead and find a worthy challenge, okay, which is Sudoku. Now, I did this last semester in class, but rather I'm going to give you guys this problem on Project Euler, which if you've not seen yet, we're going to do this. So, all right, so Sudoku, it's a Japanese meaning number place. It's a game that has a very popular puzzle concept. You can see here on the New York Times website, this is what a Sudoku board looks like. Okay, you've got a grid of stuff, right? A grid of numbers, and the idea here is to place numbers in the appropriate space. How do we do this? So Euler made a similar but much more difficult problem called Latin squares, but Sudoku is fairly straightforward, but it's simple. It's got simple rules, which makes it a good puzzle, and it's simple to understand, hard to master, which is one of those nice things that make it a very timeless kind of game and very easy for everybody. So the idea here is that we want to replace the blanks, which are zeros here, in a 9x9 grid such that each row, column, and 3x3 box contains each of the numbers 1 through 9. So here's like a typical puzzle on the left and the solution on the right. So each row contains each number 1 through 9 exactly once, each column contains 1 through 9 exactly once, and each of these 3x3 grids contains 1 through 9 exactly once. So let's move over to a bigger one to show you. So for instance, if we're trying to solve this, I cannot put 1 here because there's already a 1 in the same column, right? I can't put a 2 here because there's a 2 in my same row and in my same 3x3 grid. I can't put a 3 there because it's in the same row and same 3x3. I can, however, put a 4 because there is no 4 that basically solves the same row. There's no 4 in the same row, column, and 3x3 grid. So this is a puzzle that you normally just, logic out, right? You just kind of figure out, okay, I can put a 4 here because, we don't have something here, we don't have something here, and logically what needs to go here is this number. That's honestly the boring way to solve it. We're just going to brute force our way through the puzzle, the way to solve this. So a well-constructed Sudoku puzzle will have a unique solution that can be solved by logic, although it may be necessary to employ a guess and test method. Okay, the complexity of the search determines the complex difficulty of the puzzle. This one is an easy puzzle because you can solve it in a straightforward direction. So this is a 6K text file. And I will simply, this is what you'll do if you want a more difficult challenge. The easier challenge will just simply make a Sudoku solver. This will be the more difficult challenge, which is that here's 4. These are not 4, but we've got 50 different Sudoku puzzles over here, right? 50 of them. Okay, so you've got 50 Sudoku puzzles here. I want you to write the project builder puzzle says write a program that solves all 50 of them, and to prove that you did so, add the top 3 numbers, the top left 3 numbers together, and then give me the sum. So in other words, to prove that you solved it, you want to know we'd need to solve what this solution was plus this solution, right? What numbers went there plus what numbers went there plus what numbers went there plus what numbers went there, right? Add them all up, and you'll be able to prove that to me that you solved the Sudoku puzzle. Does that make sense? So add those 3-digit numbers. So this will have an easy version and a hard version for you as well, which is that basically we'll do the single Sudoku solver, and the other one will be a bit harder, because you'll have to read in this file, which you should have learned how to do. You can just use Scanner for that. It's not too hard. Basically, it tells you. Basically, the pattern is read in the first line, throw it away, then read in the next 9 lines into an array, and then solve that one, and then throw it away, and then go on to the next ones, and then you just keep adding the top left numbers as you go. And if it finishes, if your program finishes, you will get a solution. The issue might be is that it runs a very long time, but so why am I bringing up these puzzles? Well, because they can be solved with recursion, and that's what makes them fun. So I'm going to stop. So I'm going to stop this video and start another one because we're going to get into the topic of how do we solve these now.